Welcome back to our discussion on power series. When we met last time in our previous video, we looked at a number of different power series which were derived, which came about by modifying the geometric series. I have several of the series that we looked at listed here. So from last time, the geometric series 1 plus x squared plus x cubed and so on, we've seen several times now, converges to 1 over 1 minus x, right? And it does so on the interval from -1 to 1, right? We looked at specific examples of this many times over the last couple of weeks, and in our last video we expressed all of those various series all together as a single function, which was equal to this on the interval on which it converges, right? And then from there, what we did was we replaced all of our x's with negative x's, right? So we got 1 over 1 plus x whenever we did that on the left. But since these two series were equal, and I got this series from that one by replacing all my x's with negative x's, I'm going to get a series for this function by replacing all of my x's on the right over here by negative x, right? And we said last time that it's going to converge somewhere. It's going to converge on some interval. We never really established on what interval, right? From there, we said, well, okay, if we take the antiderivative of this function, since this function is equal to this function, an antiderivative of this function ought to be equal to an antiderivative of this function. Now, we had to be kind of careful because we weren't sure that the antiderivative that we got, well, of course, whenever we just take antiderivatives of each piece on the right here, these are the terms we get, but there's going to be some constant at the end, same over here. So I know that that this function, the natural log of the absolute value of 1 plus x, that's going to be one of the antiderivatives of this function. So it's going to be this plus a constant, but we happen to see that that constant turned out to be 0. You can look at the previous video if you want to review why that's the case. And we said that this equality is going to be true, well, on some interval. We never really established which one. However, we noticed that if this interval happens to contain the number 1, then what we have is the natural log of 2, right? Natural log of 1 plus 1 equal to the alternating harmonic series, right? Which was a fact that we talked about a couple of weeks ago, but we had not given an explanation for. Now we have an explanation for it. Of course, it only holds if this interval on which this equality is true, if this interval actually does contain the number 1, right? So the question is, how can we determine if the interval on which this series converges does actually contain the number 1? How can we determine the interval on which this series converges? And more generally, how can we determine the interval on which a general power series converges, right, for various coefficients a0, a1, and so on? Well, that's the question that's going to drive our discussion today, right? And the answer pretty quickly is that we're going to use the ratio test. And so we're going to use the ratio test to determine the interval on which this series converges. Now, just to remind you, what the ratio test tells us is that if I looked at the nth terms of this series, right, and I took the absolute value of the n plus first one divided by the absolute value of the nth one, and looked at the limit as n goes off to 0, if this limit is less than 1, then the ratio test tells us that the series converges. In fact, it tells us that it converges absolutely. Right? You'll recall that this is sort of like saying it's asking how close is this series to being geometric. Right? We're dividing a term by the previous one. We're not necessarily going to get a constant every time, but if in the limit we get something that's smaller than 1, that's good enough. It turns out that this converges. We also know it diverges if this limit is greater than 1. We don't know what happens if it's equal to 1, but for now, I just want to concentrate on this particular aspect of the ratio test, right? So we know that if the limit is less than 1, then the series converges. And for this particular series, our nth term, or the absolute value of our nth term, is the absolute value of x to the n over n. Notice I ignored the signs. Why? Well, I'm looking at the absolute values of the terms anyway. The signs of the terms kind of get in the way. They're going to get absorbed in the absolute value, so why even include them? Just mucks it up a little bit. All right, so my absolute value of my a sub nth term looks like this, and so the n plus first term has absolute value that's going to be this, right? And instead of x to the, if the third term were x to the third over 3, then the fourth term is going to be x to the 3 plus 1, 4, over 3 plus 1, 4. Right, so this is the n plus first term. And the ratio test says, well, we want to look at the limit of the n plus first term to the nth term, that ratio. And we'll eventually ask, when is that going to be less than 1? Well, let's look at what the limit is, right? So here we go. Limit of the n plus first term to the nth term is, well, I'm just putting that in for a sub n and that in for n, for a sub n. And I'm getting that ratio, invert and multiply. And just a little bit of algebra tells me that what I get is the limit as n goes to infinity of, let's see, so I have n plus 1 x's on top, n x's on bottom. So that's going to be a single absolute x. And notice also I've restricted the absolute value symbols just to the x, because that's the only thing that can change the absolute value. N's are all positive, so I don't have to worry about the absolute values of those. So I get this limit, and as n runs off to infinity, of course, this term right here goes to 1. And so what I get is just the absolute value of x. So let's look at this again. The ratio test is telling us that if this limit is less than 1, then the series converges. This limit is equal to the absolute value of x. And so instead of saying, well, this limit is less than 1, what I can say is, this limit is equal to this, I can say that if this is less than 1, then the series converges. Right? And that's exactly what I've got here. So if the limit as n runs off to infinity of absolute an plus 1 over absolute an, that's what this is less than 1, then the series converges. All right, let's analyze that just a little bit more. So that says, right, so absolute value of x being less than 1, another way of saying that is that x is between -1 and 1. Right? So if x is between -1 and 1, then the series converges. Great. Well, that gives us a lot of information, but it doesn't quite tell us everything yet. What I know from this statement right here is that the series will definitely converge on the interval from -1 to 1. It will definitely diverge whenever x is bigger than 1 and whenever x is less than -1, but it doesn't tell us anything about what happens whenever x is just 1, right? So we just don't know. We don't know yet what happens in that particular case whenever the absolute value of x is 1. In other words, we don't know what the series is going to do whenever x is 1 or whenever x is -1. We're going to have to test those separately. At this point, what I know, right? So if I know that the series converges on this interval, that means that my interval of convergence, now mind you, the interval of convergence is the interval, the full interval on which the series converges. And so far we know that the interval of convergence is one of the following intervals, right? Either it's going to be the open interval from -1 to 1. This is in the case whenever -1 does not give us a convergent series, and whenever 1 does not give us a convergent series. Or maybe it's this interval. Maybe -1 does give us a convergent series and 1 doesn't. Or maybe 1 gives us a convergent series and -1 doesn't. Or maybe -1 and 1 both are values for which the series converges. We have to decide which of these 4 is our interval of convergence. In order to do that, we're going to need to test -1 and 1 separately. All right, so let's go ahead and test them separately. Where's our series again? Here it is. So if x is -1, what does this series look like? Well, if x is -1, then what I've got is -1 minus a half times -1 squared plus a third times -1 cubed minus a fourth times -1 to the fourth, and so on. What is that? Let's see. That's -1 minus a half minus a third, right? -1 cubed is -1. So I'm going to get minus a third. Here, let's see, -1 to the fourth is +1. So +1 times -1/4 is going to be -1/4. Oh, look what we've got. We can see already we've got the opposite of the harmonic series. Right? This is the opposite of, or we could say the p series with p equals 1. We know that diverges. Right? But whenever x is 1, this series looks like, let's see, it's going to be 1 minus a half times 1 squared plus a third times 1 cubed minus a fourth times 1 to the fourth. Well, that's 1 minus a half plus a third minus a fourth, and so on. That's an alternating series whose terms are decreasing in value, and they're decreasing to 0. This converges. Right, so by looking at -1 and 1 separately, we were able to decide whether the endpoints of our interval converged. As soon as we knew that -1 didn't work, we knew that that one was out, and we knew that that one was out. Whenever we know that 1 gives us a series for which the series does converge, we know this one's out because I'm not including 1 in this interval, but we need to include 1. And so this is our winner. All right, so the interval between -1 and 1, that's the interval on which the series converges. Interval not including -1, but including +1. Right, so we call that interval the interval of convergence for this power series. Now, I want you to notice something else, right? Since 1 belongs to this interval, right? This was the original question. Since 1 belongs to this interval, we are justified actually in saying that the natural log of 1 plus 1 is equal to this series. Why? Because 1 is in our interval of convergence. So this series converges at 1, and this is what it converges to. Right, so we now have that the natural log of 2 is in fact equal to the alternating harmonic series, and we have good reason for saying that. We have lots of other facts as well, right? If I had substituted right? So we were looking at the natural log of 1 plus x equals, right? Here was our series, right? So this series is equal to the natural log of 1 plus x. Well, if x is 1/2, right? If x is 1/2, then I'm looking at the natural log of 3/2. But the series looks like, right? So x is 1/2. Here's our series. So in place of each of our x's, I'm gonna substitute 1/2. So that says 1/2 minus 1/2 times 1/2 squared plus, here's my next one, 1/3 times 1/2 cubed minus 1/4 times 1/2 to the 4th, and so on. Right. So this is a series giving us exactly the natural log of 1.5. If I wanted the natural log of just 1/2, I could have, let's see, 1 minus 1/2 is equal to 1/2. So the natural log of 1/2 could be written as, well, let's see. So this series, x is -1/2. So there's -1/2 minus 1/2 times -1/2 squared plus 1/3 times -1/2 cubed, and so on. So that gives me a series for natural log of 1/2. Now, I could have also noted that natural log of 1, well, that's what I get if I let x be 0. But if x is 0, I get a very uninteresting series, right? I get 0 minus 1/2 times 0 squared plus 1/3 times 0 cubed, and so on. Right? So I can use this fact to show me that the natural log of 1 is equal to 0. I want you to notice that 0 makes the series collapse, right? 0 is the only number that I could replace for x in this series and have all the terms collapse down to just a single number. When that happens, we say that the number that makes that happen is the center of our series. Why use that terminology? Well, if you'll notice, it's also the center of the interval of convergence, right? If we wrote our interval of convergence down here, -1 to 1, the center of that interval is in fact 0, and that's the number at which the series collapses. So that word center is really denoting where it's gonna fall in our interval of convergence. Okay. We have another terminology, another term that is important when we're discussing power series, and that's the radius of convergence. And that's simply the distance from the center of the series out to an endpoint of the interval of convergence. Right, so here's picture. So our interval of convergence was open interval, well, half open interval, open at -1, closed at 1, 0's at the center, and the distance between 0 and an endpoint is 1. So simple as that. So the radius of convergence is 1, distance from the center out to an edge. Let's revisit. Okay, so we were analyzing this series. We noticed that 0 makes the series collapse, and therefore that's going to be the center of the series, right? So as soon as we know that, right, as soon as we observe what number makes the series collapse, we know that our interval of convergence is going to be centered at that number. We also showed that, well, we were using the ratio test, and the ratio test was interested in the limit of quotients of the n plus first term to the nth term, well, the absolute values of those. And we knew that this was going to be, that the series was going to be convergent if this is less than 1. And we showed that this is equal to the absolute value of x in this particular instance. And so we knew that the series was going to converge whenever the absolute value of x was less than 1. Well, actually, we could have decided right then and there that 1 is the radius of convergence. Because after all, this is saying x is a number which is no more than 1 away from 0. Now think about that. That's another way to interpret this inequality. X is a number that is no more than 1 unit away from 0. So right away, that told me that my radius of convergence is 1. Had to be one of those 4 intervals that we discussed. Right? What we didn't know at this point is whether or not the series was going to converge at 1 or at -1, and we had to check those separately. But we saw that the series converged when x was 1, and it diverged when x was -1, and that's what told us that our interval of convergence was the open interval, half open interval from -1 to closed 1. Before we end this discussion, I want to do one more example just to solidify these ideas. Right? So I'd like to find the center, the radius of convergence, and the interval of convergence for this series right here. And I wrote out the first several terms. I expanded it. Okay. So let's see. First of all, the easiest thing to identify is the center of the series. At what number is this series centered? So again, the number at which the series is centered is the number at which the series collapses. Where does the series collapse? Well, all the terms, well, except this first one anyway, they go away in the instance whenever x is -1. Right? All these terms become 0 whenever x is -1. They collapse down to 1. And so as soon as I know that my series where my series collapses, I know what my center is. So my series is centered at -1. So I already know something about my interval of convergence, right? I already know at this point my interval of convergence. I don't know exactly what it's going to be, but I know that -1 is going to be at the very center. Now I need to know how far from -1 I'm going to have to go in order to get the endpoints of my interval. Well, let's see. So we're going to employ the ratio test for that. Let's look at the absolute value of the nth term. That's pretty clearly this, right? Again, I'm ignoring that -1. I'm ignoring the fact that my series is alternating, because that's not important here. I'm going to be looking at the absolute values of a sub n's. Why muck it up by putting the -1 in there? It just makes things look more complicated than they have to be. So I know what the absolute value of a sub n looks like, and so it's a pretty quick step to figure out what the absolute value of the n plus first term is going to look like. I'm just going to replace all my n's with n plus 1s. There it is. And the ratio test says, look at this limit. Look at the limit of the absolute value of the n plus first term to the absolute value of the nth term. And so let's see, what do we have? Well, there's the absolute value of the n plus first term, absolute value of the nth term. Why don't you pause the video for just a moment, evaluate this limit. Go ahead. Okay, did you get it? Let's see, let's do it together. So invert and multiply. I have one more 2 in my denominator than I have in my numerator. I have one more absolute x plus 1 in my numerator than I do in my denominator. And so that's going to reduce to the absolute value of x plus 1 over 2. N, as far as the limit's concerned, n is my variable. I don't have any n's there. And so this limit is just going to be the absolute value of x plus 1 over 2. And so what that tells me, remember, we're using the ratio test, and the ratio test is interested in when is this limit less than 1. Well, that limit's equal to this. And so I'm interested in knowing when this is less than 1. I know my series will converge when this, right, when the limit of the n plus first term to the nth term is less than 1, right? So ratio test tells me that that's going to happen whenever this is less than 1. In other words, it tells me that's going to be what happens whenever the absolute value of x plus 1 is less than 2. We actually know a whole lot just by looking at this information right here, because another way of interpreting this is, well, let's see, how do we find the distance between two numbers? We can find the distance between two numbers by subtracting one from the other. Let's see, if I wanted to know the distance between, say, -5 and 7, what I could do is subtract 7 from -5 and then take the absolute value, right? The distance is 12. So another way of interpreting this is as the distance between x and -1, right? I'm subtracting. The distance between x and -1 is less than 2. But -1 was my center. And so this tells me that my series is going to converge whenever x, the distance that x is from -1, is less than 2. That tells me that 2 is my radius of convergence. Right? Here's -1. And the numbers that are less than 2 units away from -1 are, let's see, here and here. So I know at this point that my radius of convergence is equal to 2. So now I know the 4 choices that my interval of convergence might possibly be. It's either going to be, well, let's see. All right, so the radius of convergence is 2. So centered at 1, radius of convergence is 2. So from there, oops, sorry, 2 units away from -1 is 1. In that direction, 2 units from -1 is -3 in that direction. So my interval of convergence has to be one of the following intervals. It's either going to not include either -3 nor 1. It's going to include maybe 1 but not -3. Maybe it includes -3 and not 1, or maybe it includes them both. One of these is going to be my interval of convergence. We have to check those endpoints separately. Well, why don't you go ahead and check it? Remember what our series is, right? Our series, here it is. And so whenever x is -3, well, whenever x is -3, x plus 1 is equal to -2. And so what I'm going to have is that whenever x is -3, my series looks like 1 minus -2 over 2 to the first, plus -2 squared over 2 to the second, minus -2 cubed over 2 to the third, and so on, right? But if we analyze that just a little bit, that's 1 plus 1 plus 1 plus 1. Well, that clearly diverges. It's a divergent series. And so I know right away that whenever x is -3, I do not have a convergent series. So I will not include that endpoint. Right? So now it's well, either the first or the second one is going to be the winner. Let's see. Whenever x is 1, what's the series look like? Well, again, here's my series. And so whenever x is 1, I'm looking at 1 minus, well, 2 over 2 plus 2 squared over 4, 4 over 4, minus 2 cubed, 8 over 8, and so on. All right, so I'm going to have 1 minus 1 plus 1 -1, and so on. We've talked about this series at length. That's a divergent series. And so we're not going to include that endpoint either. And so now we know that our winner is this first interval right here, the open interval from -1 to 1. No, that's completely wrong. The open interval from -3 to 3. There we go. Yeah. The open interval from -3 to 3 is our interval of convergence. And that's our discussion on interval of convergence as well as radius of convergence, the center of a series, and how to use the ratio test in order to determine what the ratio of convergence, or I'm sorry, the radius of convergence and the interval of convergence are. I hope that was relatively clear, and I hope that you enjoyed this video. Take care, and I'll see you next time.